Hello everybody, welcome to this session and watching this video. My name is Axel Busch and we are working on the optimization of the OpenShift performance on the C platform at IBM. And this session will be about the network performance and network performance influences of software-defined networks on microservice architectures. And we use as an example the Red Hat OpenShift container platform on IBM C. At first, I want to show you my motivation for this work. On this slide, you can see an abstraction of a typical cloud system. We see the cloud-native applications sitting on top a Kubernetes service, and they communicate to each other via an OpenFlow switch, while they communicate to the outside world via that switch and in addition to the NICs of the hardware resources. What we do know from the field is cloud-native applications are comparatively chatty. Especially in those scenarios, high latencies and low throughputs can sum up quickly. I'll give you an example. If you have 10 hops in your system, while each hop contributes with 100 milliseconds, you get 1 second in total. That's quite long. With that said, we know that we require efficient hardware and software networking technologies for best performance and user experience. Since an OpenFlow switch can be high complex, we decided to analyze and optimize such a switch, namely the OpenShift SDN of the OpenShift container platform on IBM C. As mentioned before, we run OpenShift on the IBM C platform that's typically known as mainframe system. Nowadays, it's more and more used as hybrid cloud platform like we have here with running OpenShift. The IBM System C14 machine we use for this work contains 170 usable cores, 32 terabit of DDR4 memory, and a couple of network cards like the OSA Express 10 or 25 gigabit Ethernet. The C machine is by design a highly virtualized system. You have the Prism hypervisor where all your operating system or other hypervisors run. On top of Prism, you can either run the operating system directly or you can set up another hypervisor. In this picture, CVM, where you can run hundreds or thousands of virtual machines running a separate operating system like Linux or also COS again. Summing up the feature areas of OpenShift shows us 4 of them, namely the development, deployment, management, and operation of cloud applications and their infrastructure automatically. Let's have a closer look to the 4 key areas. First of all, the management with the infrastructure, that is, the management of OCP on a public or private cloud infrastructure or other infrastructure such as the network. Then we have the core as operating system, where, for example, performance settings are adjusted to improve performance. The development can also be found in the 4 key areas. In other words, using a CI/CD pipeline for development or developing with the help of various programming languages and code repositories. The next area is the deployment of applications in containers that are scaled and need to be made highly available. And last but not least, there is the area of operations, which deals with monitoring and logging of data, but also with the provisioning of middleware or network topology. The performance of software systems is typically influenced by a set of performance influencing factors, namely the hardware, the software and its architecture, the usage context, that is, how much load is placed on the system, and finally, of course, the deployment configuration, that is, how these services of the software are subsequently distributed on the hardware. To analyze those 4 performance influencing factors, we typically use benchmarks. For analyzing the network performance, we use the network benchmark UPerf. UPerf provides several types of workloads. First of all, the request response workload we use to measure the latency of a request, while streaming is used to measure the throughput. Furthermore, we want to know how many simultaneous connections we can establish to the outside world, and how latency and throughput behave, as well as the use of different request sizes, what means how large are the packets sent over the network. Typically, we use UPerf in our regression tests for new distributions. So we have a quite good understanding of the benchmark and know how latency and throughput behave with different hardware and software setups, and this makes it very suitable to analyze OpenShift in this context. Typically, you have two systems or LPAs connected to a network. That could be, for example, OSA cards or the CVMV switch. Here, one system runs as the client and the other runs as the server, and these communicate with the packet sizes and number of connections you set up before. As a result, we get a latency in microseconds or milliseconds and the throughput in megabytes per second. On this picture, we see the system architecture of our OCP installation on C. We see two parts. On the left, there is the OCP cluster, consisting of a CVM LPAR with several CVM guests, which partly take over the role of the OCP master nodes and partly worker nodes. They communicate via the CVMV switch, which itself communicates via an OSA card. As load balancer, we use the software solution HA proxy on a separate LPAR with a RHEL 8.1 installation. And for the analysis of the external connection, we have set up another LPAR which runs with a RHEL 8.1 and on which, for example, the UPEF client or server can be executed. The deployment configuration is one of those 4 critical performance influencing factors we need to control. This means where exactly are our services of our workload deployed in the system. In OpenShift, we have 3 meter configurations, and I want to show you now 2 of them. Please regard in OpenShift you cannot run your workloads natively, but just in containers or the so-called pods. This is why we talk about pods in those scenarios. The first scenario is the so-called pod-to-pod performance, where all your pods run on the same worker. So there is no communication via the hardware NICs, but just over the software-defined network. This is a quite important use case since many microservice architectures come with very small-scale components and there is a lot of intercommunication between each other. The second scenario involves several workers. This means that the client-server workload can be distributed across different workers. This is also interesting, for example, in microservice architectures that are distributed across multiple systems. We have seen that the OCP installation and all the consideration regarding hardware, software, and workloads must be well thought, and we now take a closer look at how this complexity can affect the performance of the overall system. The following slides are always structures like this, that first the graph will be shown with the latency of the entire system, and then I show the throughput. Let's first have a look at the baseline scenario, namely the pod-to-pod performance once with OpenShift and one time without OpenShift. The green bars are the latency for the workload running in Podman without OpenShift, and the red bar is running the workloads or the benchmarks within OpenShift. What we can see here is, depending on the workload, we can get an up to 5 times better performance when running in Podman instead of OpenShift. This is very similar when having a look at the throughput. Depending on the workload, we lose about 60% of the throughput and up to a 6-time lower throughput, comparing the throughput running the workload in Podman and running it in OpenShift. What are the reasons for that? With OpenShift, we have a quite complex hardware and software stack with all those load balancers, NICs, the OCP architecture with the OpenShift SDN, the CVM vSwitch, and the Core OS. Mapped to the OCP system stack, this can be represented by such a layered architecture. At the very bottom, we have the network cards, then we have the load balancers, the CVM vSwitch, and on top of it, the Core OS operating system. The OpenShift SDN we have in addition that consists of the Open vSwitch and OpenFlow is placed on top of this. And finally, on top, there comes our application with Cryo, such as our benchmark UPerf. And as you can see, the performance of the application depends on all these layers. OpenFlow and Open vSwitch, in addition, consists of several pipeline layers and rules that determine the flow of packets in the system. And both pipeline and rules can significantly affect the performance of the OpenShift SDN, and because our application uses this, it also affects the performance. One word about the performance of the different OCP versions. All the analysis showed here was carried out with the 4.2.19. With newer OCP versions like the 4.5.13, the base latency increased a lot, up to 4 times of the latency compared to the 4.2.19. So as mentioned before, the main components of the OpenShift SDN is the Open vSwitch and OpenFlow. And the question now is how to define which pods can access other pods and or the external network. And this is defined by the OpenFlow rules, defining exactly which pod can reach other pods or other destinations inside or outside the internal network. The rules control then the communication between pods and the virtual bridges inside Open vSwitch. Besides, OpenFlow separates the control of the packet flow from the forwarding of the packets, so you have a kind of separation of concerns here. In addition, we have the channel controller that configures and manages the switch. Graphically, the system can be shown as described here. At the top of the picture, we see the controllers that communicate with the OpenFlow switch and updates the OpenFlow channel. The OpenFlow channel is exactly the mechanism that keeps the OpenFlow rules up to date, and this is exactly where the pipeline comes into play. The Open vSwitch pipeline consists of a set of flow tables, and each packet passes through the pipeline from input to output, so from left to right in the image. And each table contains any number of rules that are applied to the packets one by one. And by forwarding to the next pipeline level, the packet finds its way to its destination at the end. Now we have talked a lot about Open vSwitch and OpenFlow rules. Let's have a look at the rule. We see here an example that is comprised of 2 parts, namely status and action. Status defines if a certain packet has a certain status and then the action is applied. As mentioned in the beginning, the Open vSwitch pipeline with its rules can be quite complex. Here we can see an excerpt of the pipeline and its rules of OpenShift. Due to time restrictions, I cannot explain each and every rule, but for a qualitative view, you can see the pipeline and the rules here. Now I want to show you some results of the in-depth analysis you can find in the paper. Relevant on this graphic is rule number 1 in table 0 and the path of the packets through the pipeline, which is shown on the right by these arrows. At the bottom of the figure, we see the latency and throughput of the path. Baseline OCP represents the path that a packet must go in the delivery state of OCP4. A packet must pass through each pipeline level once, and table 0 must be passed through a second time, especially for many connections, as you can see with the turquoise bar and the red bar at the bottom left of the picture. The latency is increased and the throughput is comparatively low. Let's have a look at the shortest path we can find in the open vSwitch pipeline of OCP. By changing rule number 1 in table 0, the entire pipeline hierarchy can be skipped. You can see that the latency drops to up to 32% compared to the baseline, and also the throughput doubles in the best case. Analyzing further observes a kind of sweet spot with shortcut 1 regarding the performance, because shortening by avoid to re-enter the packets in table 0 can reduce the latency by up to 59% of the baseline. The throughput also increases by about 30 to 40%. In the paper, we described more shortcuts, shortest path, and Podman comparisons, and other scenarios. Please have a look at the paper if you are interested. Due to time constraints, I can't discuss in this presentation. Let me sum up this presentation. We have seen with the hybrid cloud platform OpenShift, it is a complex system with a complex software architecture, and we have highlighted the network part. High network performance is crucial, especially in microservice architectures, and in default configuration, we have possibilities for improvement, especially when we have performance-critical situations. Depending on the architecture and, of course, the workload, the network performance can be improved by up to 4 times, but, of course, such architecture changes require trade-off decisions between functionality and performance. If you are further interested in that topic, check out our paper. I want to thank you again for watching this video. Take care.